All right. So today we're going to be doing electron configuration. We're going to be figuring out how to determine the electron configuration of every element on the periodic table. So it shouldn't be too bad, and it's really going to be pretty comprehensive. We're going to learn about really conceptually what's going on in the atom with your positioning of your protons, your electrons, and how to determine
Now he wants to start
different properties. Hello, good morning. Yeah, so I overslept. Whoops. So just keep going. Whatever. There's only 17 of us here. Better than nobody. I expected nobody to be here. You know what I could have done? I could have just been like, yeah, no class. I could have made up like a family emergency, which would have been really bad, and then just put the lecture online, like on YouTube.
No. It's way better to hold actual class than for all of us to just get in and then you send an email that we.
Yeah. I figured that's more.
So at least we waited for something now.
Yeah, thanks for waiting. I really appreciate it. Yeah. Okay, so let's keep going. So electron configuration. We're gonna learn a lot today. Here it is. So here's the periodic table broken down into our orbitals. Remember we talked about orbitals last class. We have the S, P, D, and F orbitals, right? So here's your S, here's your D, here's your P, and here's an S also. So one S, this is helium, right? And on some periodic tables, you see helium over here when you're dealing with electron configuration, but we know it's a noble gas, so it's located over here, but it's still part of the 1s orbital. And then here's your F orbital. So we'll go over basic electron configuration just with this slide. So the way it's going to work, we'll pick an element. Let me get a periodic table real quick. There's people still joining. I got one. So we'll pick an element. We'll do fluorine. Fluorine's a pretty basic element, and fluorine's over here, right in green. All right, so this is fluorine, and in order to determine the electron configuration of fluorine and every element, the way we do it is we start from hydrogen. So we start from hydrogen over there. I'll do everything in green. Hold on. So we'll start from hydrogen, which is over here. Is hydrogen. Hold on. Still people joining. I'm sure you're texting all your friends. Oh, he's back. This class today. Because you're so enthusiastic about it. But anyway, so here's hydrogen. And the way we do it is look at the position of hydrogen. It's in 1s, and it's in the first slot of 1s. So we know that every s orbital has a maximum of 2 electrons. So just to refresh our memory from what we learned on Monday, S has a maximum of 2, D has a maximum of 10, P has a maximum of 6, F has a maximum of 14. When you get down to F, it gets a little bit weird, but we'll talk about that later on as part of the exceptions of electron configuration. But just for basic configuration, we start with hydrogen. So we write the positioning of hydrogen. And the nomenclature that we use is we write the principal energy level that's denoted by our period most of the time. It gets weird. So you see how this is period 1 and this is 1s, period 2, 2s, and then 2p on the right side. Once you get down to period 4, it starts at 3d, not 4d. So it gets weird, but I'll explain that in a minute. Remember, the periodic table is something that's invented by people. So it's our best representation of how the energy levels work. It's not perfect. And you see how F starts at 4F, and F actually belongs in here. It starts at energy level or at period 6. Meanwhile, you're still adding electrons to the 4th energy level. But we'll talk about that more later. Let's do the basics. So we're finding the electron configuration of fluorine. And the first thing you do is nomenclature-wise, you write everything you pass by, every element you pass by, the electron configuration of it until you reach that target element, including the target element. So it would be 1s. Hold on. It's 1s. Hydrogen is 1. Helium is 2. So 1s2. Then you're reading it like a book. So you're reading it, you're scanning it across. We're here. Now we go to the next energy level, or the next period, 2s2. 2s2. That's going all the way through here. And our target goal is fluorine. So we're going to go scanning across. There's nothing here. And then we have 2p, 1, 2, 3, 4, 5. That's where fluorine is. Fluorine is in 2p5. So the electron configuration of fluorine is this. Is 1s2, 2s2, 2p5. And the atomic number of fluorine is what? It's 9, right? So if you count them all up, so 9 is the electron configuration, is the atomic number. If you count up all these electrons in the exponent, if you will, you get 9. So 2 plus 2 plus 5 is 9. So that's how you can check your work to see if you have the correct number of valence electrons. So in essence, that's how you do electron configuration. It does get more complicated, and it will keep bringing little nuances onto it soon. But does that make sense for everybody?
Yeah.
Okay, cool. Pretty easy enough, hopefully. All right. So on the homework, there's a lot of questions having to do with ions. So if you want to figure out the electron configuration of the fluorine ion, let's see, fluorine minus, right? So fluorine minus, this is neutral fluorine, has this electron configuration. If you want to do fluorine anion, meaning it has an extra electron, what are you going to do? You're just going to add an electron, make it 2p6.
Well, you could just call it one of those noble gases at that point.
Oh, sorry, say that again?
If you want to do abbreviation, right? Then
Yeah,
you could just
that's
call
another
it
way to
neon.
do it. Right. So you could do the abbreviated method, which we'll talk about that later. But for something small like fluorine, you don't have to.
Mm-hmm.
And you can just do in brackets neon. But we'll talk about that later. Good job. So for fluorine as an anion, all you have to do is add an electron. And let's say for some weird reason, fluorine was a cation. Let's say it was plus. Instead of 2p5, you're going to make it 2p4. If it was a cation for some weird reason. So yeah, so you can add or subtract electrons based on the atom's charge. And then that's another configuration of ions. So that's basically how it works. We'll do another example getting into the d orbital right now, just to give you an idea of what happens there. It's really the same thing, but there are little differences when you get into some of the elements. Let's say this column's a little bit different, this column's a little bit different, and the f orbital, they're all weird. And I'll explain that in a minute, or explain that later. So let's do an element in the d orbital. We'll pick, let me see, pick iron. So iron is in, let me do 5, right? 1, 2, 3, 4, 5, 6. All right, so iron is right here. Hold on, 1, 2, 3, 4, 5, 6. So iron's right here. It looks wrong. That's right. Okay. So this is iron. So we do the exact same thing. We start from hydrogen. We go 1s2. 1s2. Then we go through 2s2. Then we go through again 2p6. We're going all the way through 2p this time. And then we go to 3s2. Then we keep going across 3p6. Then we go 4s2.
I'm in your account.
And then we end up at our target element of iron. We go, now we are in a 3D. 3D, 1, 2, 3, 4, 5, 6. So 3D6. So that's the electron configuration of iron. Any questions on that? So they're all basically following this basic pattern of just reading through the periodic table and writing the energy levels that you pass by. Now, one of you asked before about the abbreviation. So this abbreviation that we're talking about, it really makes it easier for us to write the electron configuration of larger elements. So let's say we were writing the configuration of something in the 5f orbital all the way down here. That would be crazy. This is 5f, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? That means we'd have to write the electron configuration for everything that it passes by. There's over 100 electrons, and there's a lot of writing to do. There is an easy way to do it. So let's take iron as our example. So this is equal to iron. What you can do is what you call a noble gas abbreviation. So the noble gas abbreviation, you basically count backwards from your target. So iron's our target, and we're going to count backwards. We'll start at iron, we'll go back, and then we end up at 3p6 right here. So at 3p6, it's a noble gas. And the noble gas that it is argon. So what we can do is we call it our noble gas abbreviation for configuration. So it's argon. What we can do is we can write in a bracket argon. And then we could write whatever else comes next. So if you look at argon, it's at 3p6. So then going next, you have 4s2. And then going after that, you have 3d6. So this is also an accepted configuration for iron. This is also equal to iron. And they're identical. So either one on a test is perfectly acceptable. Sometimes I may ask you for the abbreviated, or the homework might, or something. But if it doesn't specify, you can put whatever one you want. So you see how putting this argon in brackets is equal to 1s2, 2s2, 2p6, 3s2, 3p6. Just like that. And then you write whatever's left. Okay, good. So, yeah, that's it for now on that. So, are there any questions on the basic configuration? And we'll talk about why it's a weird, in terms of the numbering. It's not, the whole fourth period isn't 4. It goes 4, then 3, then 4. That can get kind of weird. Just, if you remember this, here's what I always tell my students, is that S starts at 1, P starts at 2, D starts at 3, F starts at 4. If you remember that, you'll be good, because if you know where the orbitals are, S starts at 1, P starts at 2, D starts at 3. This is 3D. And F, as soon as you hit an F orbital, it starts at 4. That's easy. And also, the reason why we learn quantum numbers first, this corresponds to our quantum numbers. Almost. Well, kind of. Well, it does. Because the first time you see an S orbital is energy level 1. Because if n equals 1 for our quantum numbers, L, the only value for L is 0. That's an S orbital. If n equals 2, our possible values for L are 1, plus 1, 0 and 1. If that's the case, that means energy level 2 can have an S orbital and a P orbital. So that's why you see P the first time is an energy level 2. For n equals 3, our possible L values could be 0, 1, and 2. L equals 2 corresponds to a D orbital. That's why energy level 3 is the first time that a D orbital appears. N equals 4, same thing. Our L values could either be 0, 1, 2, or 3. And then our L value of 3 corresponds to the F orbital. And that's why energy level 4 is the first time you see an F orbital, because of L equals 3. So does that make everything kind of connect from last class? So that's why we learned quantum numbers first, kind of the positioning of electrons. Now we're going to learn how do we apply that to the periodic table. And it is by doing the configuration. So, yeah, I guess that's it for now. Okay. Well, we can talk about the quantum numbers soon. This is going to relate to it now. So there's other ways to write the orbitals. Now, the configuration is one way to do it, and that's the most comprehensive and the easiest way to do it. But there's another way called the orbital diagram. So the orbital diagram is represented by, it's very easy to convert one to the other. It's converting, let's say hydrogen is 1s1. That's the configuration of hydrogen. And you're basically writing in a block each of the subshells for the orbital. And we know that S has one subshell. That's why there's one box. And we know that hydrogen only has one electron, which occupies only one of these single single-headed arrows in that one box. So that's a very simple idea of this orbital diagram. The reason why we have these orbital diagrams is from an electron in the orbital diagram, we can directly tell all of the quantum numbers from it. So if I looked at the electron configuration and I saw that iron has an electron in 3d6, I can't tell you any of the quantum numbers except for quantum number N, which is 3, and L, which is 2, because it's in the D. But in terms of the electron positioning of electron number 6, I can't tell you anything. But we can actually figure that out from... I dropped my pen. I dropped my pad. Hold on. Hope it didn't break. Great morning for me. I'm falling apart. All right, there we go. So from the orbital diagram, we can actually figure out all of the quantum numbers from an electron in an atom. So let's do iron as an example. We'll only pick the last orbital of iron, or the highest energy orbital, which is the d orbital. So it'd be 3d6 is what we're trying to figure out. So first we can write this is called the orbital diagram. Orbital diagram. So in the d orbital, we know there's 5 subshells. And how do we know this? Because we know that d holds a max of 10 electrons. That means if every subshell holds 2, there has to be 5 subshells. Does that make sense? I don't think I've said that as many times as I'd like to. That each subshell holds 2, and let's say for S, there's 1 subshell. For P, there's 3 subshells. For D, there's 5 subshells. And for F, there are 7 subshells. So if that's too much, you could ask questions, but that's the info. So knowing that D has 5 subshells, and we want to occupy the d orbital with iron's amount of electrons, which is 6, here's the way we're going to do it. So we're going to draw 1 arrow. And then this is called the off-bow principle, where, and I call it the open bus seat rule. When we're doing these orbital diagrams, we don't just do this. We don't just fill the electrons in like this. There's 6 of them, so it'd be like that. That's not right. And the reason why that's not right is because of energy. And a lot of the things we're going to talk about today with electrons and electron energy level and configuration and why there's going to be a lot of exceptions to this, to electron configuration, but we'll talk about why that makes sense energetically. Because basically the answer for everything is it's not energetically favorable, so it doesn't work. If we did that original configuration that I wrote with all the electrons kind of packed together in the first three subshells, the repulsion of the electrons would be too much, and it wouldn't be energetically favorable. You can force it with a lot of energy. You can force anything with a lot of energy. You can make iron become an anion with a lot of energy, but it's not energetically favorable, and it wouldn't last long without a lot of energy. So energetically favorable is the goal of everything in the world. So you want to be at a least energetic state in order to be stable. That's the goal of every molecule in existence. So the way iron does it with its electron configuration is the first electron stays in the first subshell. The second one wants to be further away, so it stays in the second subshell. The third one, third subshell. Fourth one, fourth. Fifth one, fifth. And you notice that they're the same arrow. Arrow's going up. The reason why the arrow is going up, the arrow tells you what's going on? Okay, the arrow tells you the spin. So remember that quantum number? ms. So quantum number ms could actually be determined using this orbital diagram. So one spins in one direction, and then you're adding your 6th electron, since we only added 5, that would spin in the opposite direction, like that. So that represents our orbital diagram for the 3d orbital in iron. And I call it the open bus seat rule. So an easy way to remember that is let's say you go, or a train, whatever. Let's say you go on a bus. You walk in the bus and there's nobody, it's empty. What are you gonna, and you're lazy. What are you gonna do? You're gonna sit in the first available seat by the window or whatever. Then somebody else walks in. What are they gonna do? They're gonna see you at the first seat. It's weird if they sat next to you because people don't like other people. So they sit behind you. And then next guy comes in and sit behind him. Next guy comes in behind them. Eventually, you have someone sitting in the back. And then if someone else comes in and every seat is taken by one person, he has no choice, or he or she has no choice but to sit in the next available seat, which is in the front next to somebody. Being energetically favorable, meaning they don't want to walk all the way to the back to do that. So they want to sit in the front, but there's somebody already there. They have no choice energetically because they want to conserve energy. So they sit next to them. So that's the open bus C rule. And then eventually you can fill the electrons, one here, one here, and all the other subshells. Five subshells. Yeah, and you notice how the arrows are opposing. And this is because of the spin. That if you're in the same subshell, the only way to be energetically favorable for electrons is if they're spinning in the opposite direction. Now, it doesn't matter if all of your arrows are pointing down for the first electron in the subshell. The only thing that matters is they're all in the same direction. So if you have one of these going down, that's not right. They all need to be going in the same direction. And when you add a second electron to it, it needs to be going in the opposite direction as the first one. So that's it. Okay, any questions on that? Okay, so going forward, that's really the Pauli exclusion principle of they need to be opposite spins. And then, yeah. Okay, so if there's no other questions, we will continue. So the next very important concept that we're going to learn about is, well, I actually taught electron configuration and orbital diagrams in like 4 slides. That's pretty good. I thought there'd be more slides on it. But the next thing we're going to learn is shielding an effective nuclear charge. Now, this concept is important to understand the different trends we're going to go over. We're going to go over ionization energy, atomic radius, and electron affinity as our 3 main trends in the periodic table. We'll learn about that soon. But we need to understand first effective nuclear charge and what that means. So we can read this. So basically, if we know that every atom has multiple electrons, except for hydrogen, we know, but most of them do. So each electron in a multi-electron atom experience both attraction to the nucleus, why? Because it's positive, and repulsion by other electrons in the atom. That's true, right? So this balance of repulsion and attraction to the nucleus, repulsion by the electrons and attraction to the nucleus, make this effective nuclear charge. Meaning, what you have to do to figure out what the effective nuclear charge is take the perspective of an electron. What do you see when you look at the nucleus? How many electrons are shielding you from the nucleus? And how much of the nucleus are you seeing in terms of how much positive charge are you seeing? And that's called the effective nuclear charge, is how much nuclear charge are you seeing? So here's an example. Now, let's say we are this electron. If we're looking into the nucleus, what are we seeing? And keep in mind, these electrons are not stationary. Just like we talked about the way they move in last class in terms of their probability distribution, they move all over the place. They're moving extremely fast. So they kind of think of them as an electron cloud. That's why this cloud is in blue, right, in light blue right here. These electrons are moving extremely rapidly to the point where they're in all of these locations at the same time, virtually. Basically, this whole cloud is a cloud of -2. Think about it like that. Think about it as the nucleus is the sun, and the electron cloud is a cloud. The thickness of the cloud will determine how much of the sun you see. That's a perfect example. Wow, that's a really good example. That's a really good analogy. I just thought about that now. But basically, if we're taking the perspective of one electron we're going to see what do we actually see. And it says right here, you experience a net charge of about +1. And the reason why, the nucleus is +3, so this must be a lithium atom. And then the electrons in front of you or closer to the sun, let's say we're on Earth and then we're looking at the clouds. The cloud has 2 electrons, 1 and 2. They're all moving in here. So we see +3 -2. We see +3 -2, which is equal to +1 as our effective nuclear charge. Okay, does that make sense? All right, I hope it does. So the next type, well, the next, not really type, you can also figure that out if you are an inside electron that is penetrating the clouds. Let's say it's a really thick cloud, but you're in a plane and you're above the cloud. You can see the sun directly. That's exactly the same concept. Now, if you're this electron, you have other electrons in higher energy levels. They're further away from you, creating this cloud. But you're already inside. So you directly see the +3 charge from the nucleus. So you could say that your effective nuclear charge of this electron is +3 because you're close to it, and the electrons of higher energy levels are around it, around you or further away. So that's effective nuclear charge. And there's actually an equation for it. So the equation, I'm not going to give you on the exam, but it's very easy to understand conceptually. Don't memorize equations. So basically what it says is that Z effective, meaning the effective charge, is equal to the Z, which is the charge of the nucleus, or the proton number, or the atomic number, proton number, atomic number, whatever, minus S. S is the electrons in lower energy levels. Basically, how many electrons are in front of it or in the cloud in front of you. So that's how you figure it out. So it's the number of protons minus the electrons that are in front of you, blocking your view of the sun or the nucleus. Okay, and the way this works in terms of energy level, really, it's how much energy each energy level has, is in this path. And this is why, this is not why, oh yeah, this is why energetically speaking, the periodic table goes from 4s to 3d. And that's why you include 4f somewhere in the middle, right? After 6s, not after 6, or not after 4p or something like that, or 4d. So this is why it doesn't work conventionally, right? So we know that from the periodic table, let's just refresh, we go back, that when we're reading the electron configuration, we go from 4s to 3d. That's weird. You don't go from 4s to 4d. D starts at 3, for this reason I was saying before with the quantum numbers. And also that makes sense energetically. So we'll talk about that. We'll go back to this slide. Okay. All right. So here's actually, we'll look at this one. This is the whole thing. Okay. So this is the energy levels. Now, if we go in terms of increasing energy level, because the way electrons want to add the way atoms want to add their electrons is, like I said before, in an energetically favorable fashion. So we want to start out at the lowest energy level, and then as we go forward and we have no other options, we want to put electrons on higher energy levels. So that's exactly what you do. You go from 1s2, 2s2, 2p6, and these 3 dots represent the subshells. 3s, 3p, 4s, 3d. Notice how 3d is over here. It's not where 4d is a lot higher energy. It goes 3d, 4p, 5s, 4d, 5p, 6, blah, 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 etc. And then here's where you get the f orbitals up here. So this is how it works. Now, a good question would be, oh, how come once you add electrons to the 4th energy level in 4s, that the atom feels comfortable then adding more electrons to the 3rd energy level? Since these numbers represent the principal energy level n, don't you want to add them in increasing energy levels? And then generally you do. But when you get to
It takes more
4s,
energy to do that.
it does. Correct.
They
Correct.
just want to do the path of least energy.
Exactly. So it does. But also I think last semester that's the answer, right? Because you always want to add increasing energy. But in terms of the actual level, 3, 4 versus 5, whatever, 3 versus 4, how come when you're on 4 you want to add to 3? And yes, the real answer is because of energy, because 3D happens to be a lower energy level than 4P. But the question is, why is 4S a lower energy level than 3D? So,
Because S has like less orbitals, doesn't it? Like S
yeah,
has
it only has one subshell. That's
Okay.
that's one reason. It only holds 2 electrons, so it's going to be less repulsion there than in a d orbital. But so the real reason, I mean, that's correct. That's partially correct. But energetically speaking, if so, the 3. Let's look at it this way in terms of actual positioning. So this is the nucleus. You have energy level 1, energy level 2, energy level 3, energy level 4. So in energy level 3, when you get from 3s to 3p, you're going to have 8 electrons. Then you have 4s, you're adding on to more. But then, like you were saying, to add to 4p, you require a lot of energy. But 3D, there is still physically room that would require less energy than adding to the new energy level. So the way I like to make an analogy of it is, let's say you have 2 suitcases and you're filling them for a trip, and you don't know how much stuff is going to go into each one. So you fill up one, and then you fill up the other one. You still have more stuff. So you're going to fill up the second one until it's at capacity. And then what are you going to do with the remaining stuff? You're going to go back to the first one, and you're going to fill it even more because you thought, oh, this one's considered to be full. But then when you realize there's a necessity to put more in there, you're going to try to go back and put in more if there's room. So that's what the electrons do. They're like, all right, 4p is the target, but then there's still room in 3D, so I don't have to start a new suitcase yet because it's easier to do this. So that's exactly why. So yeah, thanks for the participation, by the way. I'm sure some of you are, but some of you aren't. But thank you for those of you who are participating. Okay, so that's that. I can talk about that all day. All right, so we understand that concept. Here's the PR table again, and here's orbital filling. So we talked about all this already. Hund's rule, we talked about it. We talked about how you fill the orbitals by the open bus seat rule or by energetic favorability, meaning if you go from boron to carbon to nitrogen and you keep adding electrons in the 2p orbital, boron has 1, carbon has 2, so you're going to add 1 and 2. Nitrogen has 3. And then oxygen will then have 4. So oxygen would go here. And then fluorine will have 5. You put it here. And then neon will have 6. And it'll be completely full. And you put it there. So that's how that would work. And then here's another representation of the energy level. So some of my students find this easier to understand rather than memorizing the periodic table, that they go from 1s all to and then 4s to 3d. If you don't want to memorize that, then if you write 1s through 8, even though there is no 8s, you write 1s through, really just write, I guess you have to write it because you have to include these, but 1s all the way down to 8, 2 to 8, 3 to 8, 4 to 8 for F, and you just write diagonal lines that will represent the energy level. So you go 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, and you go like that diagonally. That's also correct. But whichever way you want to remember it, me personally, I don't want to think about this chart every time I'm doing electron configuration. So I rather just look at it through the periodic table and practice it because it does make sense. Okay. So any questions? No? All right. So now we're going to learn about the infamous F orbital. Wait. Yes, we're going to learn about that soon. But let's talk about it now. So the F orbital. You know what's weird? Not every periodic table is the same. Some periodic tables include these two elements, lanthanum and actinium, in the d orbital, like this periodic table does. Some of them are in the f orbital, like other periodic tables do. Like, not this one, but some of I have seen it. Maybe these are all consistent because they're from the same textbook. But some textbooks actually show lanthanum and actinium in the f orbital. And there's actually a discrepancy in teaching chemistry, whether it's good to teach lanthanum and actinium in the d orbital or the f orbital. And the reason why, why isn't it definitive like everything else in science? Because the energy levels of 5D and 4F, and similarly 5F and 6D, are so similar in energy that some experiments have determined lanthanum to be actually in the d orbital. I mean, it's electrons in the d orbital, and some experiments have determined the energy to be in the f orbital. So if we go back, this is a good representation of how close, once you get to the top, how close they are in energy. So 5D and 4F, look how close they are. I mean, this is somebody drawing dots, but it's true that the 4F and 5D orbitals and 5F and 6D, hold on. So these are very close in energy. So it makes sense that these electrons from 4F could skip to 5D and vice versa. The 5D electrons could totally be in the 4F. There is not much difference in energy level at all, and it's sometimes it's a negligible difference. So these electrons, once you get down to doing the configuration of the f orbital, 4 and 5F, it gets really weird. So
wait, how many boxes does the F have?
The F has 14. So in terms of boxes, there's 14 elements here, meaning the maximum electron it can hold is 14. But in terms of the orbital diagram, like this, there's going to be 7.
7, yeah.
Yeah.
So it's just half of what it can hold.
Exactly. So the way you're doing orbital diagram, it's a perfect way of saying it. So like it's half of the amount of elements there are. So this one's going to have 1, this one's going to have 5, this one's going to have 3, this one's going to have...
right.
7. Right. Good. Okay. So this is a really good periodic table because it shows electron configuration for all the elements, basically. And once you get to the last two, it only shows the last two orbitals of filling, but it's still really comprehensive. Now, if you get down here, obviously for cesium, you're at 6s1. For barium, you're at 6s2. That makes sense. At lanthanum, you're at 6s2 5d1. That makes sense also. But then you go to cerium, I think, for 4F. Instead of 4F1, it's 6s2 4f2. So it completely skips over this first d orbital, and it goes to 4f2. So that's weird.
But F comes after D, right?
Exactly. Oh, no, okay. No, F comes before D. Sorry. F comes before D.
It's SPD FD.
It's weird. So when you get to here, so the way it works, so that's why I don't like teaching that. It's a weird discrepancy. So I'm never going to give me the electron configuration of lanthanum. It makes sense, but that's why I like including lanthanum and actinium in here, because
that's how it does it in most.
Exactly, yeah. So the f orbital is before the d orbital. It is. That's how you're going to write. You're going to write 6s2 4f whatever, and then whatever's left over. Because in terms of the number of electrons, that is true. But for lanthanum and actinium as elements, their their electrons are in the d orbital. Their last electron is in the d orbital. You see 5d1, 6d1.
Mm-hmm.
I like to teach that as, oh, they're include them here and just put this whole thing right here. That's easier to understand. And just view them as exceptions. They're D1 and D1 rather than putting them here and then viewing the whole F orbital as a weird exception where it goes, like you were saying, does it go D, F, D? That would be way too confusing, and it doesn't. So basically, I'm not going to give you these as an electron configuration. I might ask the expected configuration. So what that means is, what is the expected configuration of ND? The answer would be everything, and then 6s1, 6s2, 4f3. That would be it. Because if you add up those electrons, well, see, it's 4f4 actually, but the expected would be 4f3 because it takes one from this d orbital that's not really a d orbital, even though it's in the third spot of F. It's weird, I know.
I'm a little confused. So is it S, P, D, F in terms of energy?
Yes.
Okay.
But lanthanum and actinium have their last electron still in the d orbital, even though they're technically part of, they come before F. Even though D comes after F, just these two elements come before F.
Okay.
Okay. So if you can remember that, okay. If not, I'm going to ask the expected configuration, meaning just going through 6s2, ND would be 4f3 because it's in 1, 2, 3, third spot. Okay. So then you see how it gets weird. You can take a look at this on your own, but you see how it's weird. It starts at 4f2, not 4f1. Then it goes 3, 4, 5, 6, 7. That makes sense. But then, oh, wait, look. It goes 4f7, 5d1. That's weird. And then it skips 8, and it goes to right 4f9. And then 10, 11, 12, 13, 14. And then at the 14th element, it goes 4f14, 6d1. Not 5d1, 6d1. Same as this one almost. So it's really weird. And this is why they can jump. It's all over the place. There's another discrepancy in teaching chemistry where this one, luthium and lawrencium, or whatever they're called, they are also in the d orbital because they have d electrons. So people are like, oh, I like lanthanum and actinium in the F and these in the D. Some people are like, I like lanthanum and actinium in the D and these two in the F, which I like personally. Because we know that I like to teach that F comes before D, and then this is where the D kind of starts, is luthium and lawrencium, because they have D electrons. But also, lanthanum and actinium have D electrons. So again, I can talk about it all day. It's weird, but just know that it goes 6F, or in general, it goes 6S2, 4F14, and then 5D10. Okay. All right. There's another thing that's weird, or it makes sense. So a lot of these weird things that aren't consistent in the F orbital can be explained by the filling of the subshells and the energetically favorable filling of the subshells. But there's a lot more in there to explain than there is in the simpler examples of that. So I guess I'll just talk about it now. Yeah. So in these here, we notice something here. I'm going to circle things here and here. All right. In these two, this is D4 and this is D9. We notice something. And what we notice is, look, it goes from 3D1, 3D2, 3D3, 3D5. This one's also 3D5. That's weird, right? But that is a consistent exception. You see that with D4 and D9. You also see that with F7, F6, This is technically F6. And then you notice they have F7. And also you see that with F13 is that they have F14. So, but let's talk about these first. These are fair game for the exam. Now, the reason why this has an exception, and look, you see it's 4s1, 3d5. So you can think, all right, these are all 4s2. That means when you get to chromium, one of the electrons from S is being taken by 5d, or by d5, by 3d. And yes, that's exactly true. So if we write it down, this is going to be your 4s. Your 3d is going to be 1 box, 2 box, 3, 4, 5. I know it's sloppy. What happens is when you have 3d4 or any d4 and you have 4s2, and this is the configuration, this is the expected configuration at the ground state. And you want to add another electron, or you have the right amount of electrons here. It is more energetically favorable to have this last subshell filled up by 1 electron than to have 2 electrons in the 4s energy level next to each other, making that repulsive force. So what this electron does is like, I don't want to be next to you, and it wants, oh, I just clicked the button on accident. What did I do? Oh. I just closed it. Oh no. Perfect day. I'll open it again. There shouldn't be a close button on this notepad. It's weird. All right, so let's go back. Where were we? We're here. All right. All right, so we're going to 4s, 1 box, 3d, 1, 2, 3, 4, 5. So it makes sense that energetically the 4s doesn't want 2 electrons in there. That second electron will have a lot of repulsive forces to the first one, and it would rather fill the 3d completely. So like this. This is more energetically favorable. Wait, what happened?
Professor?
Yeah.
There's nothing getting cast to the screen right now.
Oh, okay, I'm sorry. Ta-da. There we go. So thanks for telling me. There is nothing energetically favorable, or this is the most energetically favorable with this many electrons, is that 1 electron's in the S because it doesn't want to feel that repulsive forces from the
What element are we talking about, sorry?
Oh, I was talking about these.
Okay.
Yeah, and I'll talk about these in a second. Let's do that again. So yeah, these, you have the D9 elements and the D4 elements. They follow this weird exception, but it makes sense energetically. And so do these.
Yeah.
Yeah, and these.
Because it's right above the halfway point and the filling point.
Exactly.
Okay.
Right before the halfway point. Yeah, so it wants that extra electron. In this case, in the F's case, it's taking that extra electron from 5d1, not from the S. Since they're so close in energy level, it doesn't make much of a difference. But we'll talk about the D1s first. So does this make sense? Where the 4D, the D4 elements like to take an S electron because it makes it more energetically favorable to be in this position where everything is filled by 1 electron in the D orbital, that position versus having an open spot with 2 electrons repelling each other in the S orbital.
Yeah, that can make sense if you study it enough.
Yes, good. So that's, if you study enough, it should make sense. Then the same thing is true for D9, because with the same concept, something like this is not energetically favorable because a 3D orbital has a higher energy level than a 4s. So you would think, all right, it makes sense that there's no electron here because you don't want to put an electron in a high energy level. But for an orbital to be filled up actually makes it more favorable. So if you have a higher energy orbital that's filled up versus one spot remaining, it is better energetically than having a lower energy level, or sorry, a lower orbital, a lower energy orbital being half filled. So the s orbital would be like, all right, I don't want this electron. I'll give you this electron to make the 3D more energetically stable, because it's good to keep our high energy orbitals more stable. So having that one spot open would not be a good thing for that. So that's why the same thing occurs for all of the D9 elements. You see copper, it goes from 4s1, 3d10. Same thing with silver, and same thing for gold. It goes to D10. And then zinc, cadmium, and mercury, they follow our traditional patterns where they're filling everything. So it would be 4s2, 3d10, rather than 4s1 like copper. So these are two exceptions that I expect you to know, and they are fair game for the exam. The D4 one, it doesn't hold true for tungsten and whatever Sg is. So I just keep that in mind. But for chromium and mobilium or whatever this is, yeah, they hold true. And then same thing here with europium, americum, and then yttrium, and I don't know, whatever NO is. So they follow the same trend, but they take their electron from lanthanum's configuration, which is 5d1, 6d1. So they would take a d1 electron and they would put it towards their F to make their 7 boxes, their 7 subshells of F completely filled by one electron. Same thing here. They would take one from the d orbital and make their F orbital completely filled right here to 14. So knowing that, that's really all the exceptions there are for electron configuration. Everything else is pretty straightforward. So yeah, are there any questions on that?
No.
Okay, cool. So another little thing is you can actually determine the valence electrons, and this is going to be on either, or definitely fair game for the exam, but it is going to be on the homework as well, is determine the valence electron configuration, or the configuration of the valence electrons, or how many valence electrons there are of an element. And we know how to do this of the main group elements. But if you look at something like this, let's look at a full configuration. Here. Nah. I'll write one. I'll write fluorine. I'll write fluorine again. Are you hiccuping? I hear hiccuping.
Someone's got to get burped.
Yes. So I'll write fluorine configuration 1s2, 2s2, 2p5. Now to figure out the valence electrons, what you do is basically take the definition of a valence electron. It's the electrons that are furthest away from the nucleus, right? So they're with the highest principal energy level shell, meaning the highest N. So if we go back to our configuration of fluorine, which electrons have the highest N? It's going to be N equals 2. It's going to be these two orbitals. So we add those up, 2 plus 5, and we get 7. And that makes sense. Fluorine is in 7A, 7 valence electrons. So that makes sense. Where it could get complicated is if we're dealing with something like this. You have 4s, 3d. Now, even though 3d energetically comes after 4s, the valence electrons are only going to be 4s. It's based strictly on the energy level 4 being the highest, not 3. Because these electrons are actually located closer to the nucleus than the 4s ones. So in this case, your valence electrons would be 2 if that was filled up all the way, but hold on. So let's say it was like this, just 1. Then you'd have 1 valence electron, even though your configuration has 1 here and then 10 here. It would only be 1. So whatever the highest principal energy number is, that's going to be your valence electrons. Okay. Any questions? So we went over this already. We went over noble gas configuration. We went over that. We went over that. We went over anions that you just add electrons. So like the sulfur at ground state is 3p4. If we want to make the sulfur 2 minus, it would be 3p6. So you add 2 electrons to it. So also there's a little thing. Remember we talked about last class how electrons can be excited from energy, photoelectric effect, or from different kinds of energy, electromagnetic radiation, whatever. They can be excited to different energy levels. And they can be excited to different orbitals as well. So just to let you know, not really, there's not going to be any questions on this, but just be aware that electrons can jump all the time. If this is carbon at a normal ground state up here in black, if you give these electrons energy, they can totally jump. They can jump. This one can go back here to a less energetically favorable state. They can go one from here to go to here. They can jump, and then they can come back down to their ground state and emit energy, just like we saw before. Okay, so the next definition, so we have this, and then we have the periodic table trends, and then that's it. So the next thing that we're going to talk about here, a very brief thing, is paramagnetism and diamagnetism, or diamagnetic. Basically, paramagnetism means in the electron diagram, you have unpaired electrons. That's it. Diamagnetism means you have all paired electrons. So para, unpaired. So that's how I remember it, is think para, unpaired. And dia, paired. Like that. Okay, so there is a couple questions of that on the homework, but that's pretty simple. I mean, if you have, so carbon in the ground state is going to be diamagnetic because, wait, no, it's going to be, sorry, it's going to be paramagnetic because it has 2 unpaired electrons. Carbon in this state, this energized, excited state, is going to be diamagnetic, meaning all the electrons are paired. And then here, paramagnetic again. Okay, so you can do this, write the electron configuration of the copper atom as 2+. So we'll do this together. Actually, no, I'll give you a couple minutes. Yeah, so I'll give you till 10:33. This will give you something to do. I've been talking the whole time. Okay, so we'll give it a try. So copper 2+. So we know copper is one of the weird exception ones. So copper is right here in 3D9. So here's copper. We'll take its configuration and we'll put it right here. So here's copper at the ground state. Because we know it takes, wait, no, nope. This should be 10. And this should be 1. So here's copper. So what it's going to do, and we'll write it. So here, we'll make this easier. We'll do the orbital. So it's 4s, and then here's 3d. So 1, 2, 3, 4, 5. Okay. So you have 4s1, and then you have 3d10, so we'll fill that up quickly. Okay, cool. So now we are going to make the copper 2+ cation. So if you have a cation, you are going to remove electrons because you want to become more positive. So the first electron we would remove is the valence electrons, because we know that if we make ionic bonds or make ions, the valence electrons are the first ones to be removed. So the first one that would go is 4s, because that's a valence electron. Now, our valence electrons, our highest energy, are here. So we would take one away from here. And that's it. So your final configuration would be 4s0, 3d9. So that would be this one. Ta-da. Not any of those. All right, any questions on that? So you always remove the valence electrons first. Okay, continuing. Now we're going to learn about the periodic table trends. There are 3 trends. There's atomic radius, ionization energy, and electron affinity. Now, to understand these, I'm going to write this little note down, that we need to keep in mind certain things. We need to keep in mind effective nuclear charge, orbitals, and proton number. So these are things that we need to focus on when we're making sense of the trends. It's one thing to memorize the trends. It's another thing to understand why they work. And if there's a weird exception, to be able to explain it. And knowing what we just learned of the concepts of effective nuclear charge, positions of electrons in the orbitals, and the number of protons will explain that, will help us explain. So the first one is the atomic radius. So atomic radius is, the radius of the atom, right? So let's just cut to the chase. Here's the trend of atomic radius. So the atomic radius, it increases going down the periodic table. And this is all generally. Of course, you can find exceptions. Increases going down. I think there's any exceptions with that. Not really. Oh, yeah, here's one that's decreasing going down, aluminum to gallium. But there's some little exceptions, but for the most part, it follows suit. Then it decreases going towards the right. And the transition metals, they're always in the air because they're all very similar. And again, this is a human-made thing where with the transition metals, they really had nowhere else to put them. And same thing for these metals over here. They're kind of just, they follow it a little bit, but not really. So you have a decreasing radius generally going this way, going to the right. And the reason why is because of the protons. So what happens, let's go from, we'll do lithium, beryllium. We'll do this level, lithium, beryllium, boron. So lithium looks like this. You have 3 in the nucleus, and then you have some electrons, and you have 1 electron and 1 valence electron there. Beryllium, you're adding an electron, but then you're also adding a proton. So now the proton charge of the nucleus is going to be +4. So you're putting electrons out there, but you're also increasing the charge of the nucleus. The main thing here for atomic radius, increasing the charge of the nucleus brings the electrons closer to the nucleus. That makes sense, right? It's a higher effective nuclear charge, and it's a higher attraction, which same thing. So it's a higher effective nuclear charge. That's the main reason for atomic radius. So that's why it decreases going to the right. The reason why it increases going down is because, well, the atoms get bigger. So rubidium is huge, has the biggest atomic radius. It goes all the way up to, it has 7s. It covers every single energy level. And it only has one valence electron in the 7th energy level. And it has a lot of protons. How many? Let me see. Oh, there's actually more. Rubidium's not the highest. Rubidium's the highest on this chart. Francium's the highest. Rubidium has 37 protons. So it has a plus 37 nuclear charge. So the electrons on the outside aren't really going to be seeing much because they're shielded by a lot of the inside electrons. So rubidium is only going to have one electron out here. Meanwhile, everything else is happening inside. So its effective nuclear charge will only be +1. So it'll be attracted not too much to the nucleus. But then when we get the strontium, the effective nuclear charge increases because you have another electron next to it, but the proton number increases as well, bringing them closer to the nucleus. And then same thing happens when you go across the table. So basically, you have the increasing size to the left or decreasing size to the right and increasing size going down. Does that make sense? Here's another chart saying the same thing. And here's another chart saying basically the same thing. And you see in each period, going from, let's say, lithium all the way to neon, let's say all these different periods, you see that the radius decreases and then decreases slowly, and then it reaches the noble gas. Then it starts out really high again because you're opening up a new energy level. So that means you add another shell. Then it gets a lot bigger. Then you eventually close that shell down by adding protons, bringing the effective nuclear charge higher, squeezing it until it's at a noble gas. Then you add another shell, squeeze, generally, and then you add another shell, etc., etc. So does that make sense? Okay, good. I hope it does. Next is ionization energy. So ionization energy is the energy required to pull off an electron, and it's positive. So meaning you have to put in, let's say, this random X gas, let's say sodium gas. In order to take an electron off of sodium gas or any gas, it requires to put in energy. So how much energy per mole is the ionization energy? So for sodium, it happens to be 495 kilojoules per mole. So that's a decent amount, but it's not very large. And we'll see the trend. Also, it forms a cation. And another thing is, cations are always smaller than their corresponding atom. And the reason why is because you're losing an electron, so you're basically losing you're losing a shell, basically. So when you're dealing with, let's say, any of these, really, any cation, what you're doing is you are getting rid of the s orbital. So magnesium, even aluminum, you're taking out 3 electrons, you're getting rid of the s orbital completely, and even going into the p orbital for aluminum. But you're getting rid of the entire, you're getting rid of electrons that occupy the highest energy level. So you're losing valence electrons. Basically, things we know already. I'm just saying them in different terms. Losing valence electrons, if you lose all of your valence electrons, just like these cations do, you are losing a principal energy level. So the atom will generally get smaller. And usually it decreases a lot. It's probably a 2-fold decrease going from the ground state atom to the ion, about. Sometimes even almost 3. But usually it decreases by half the size. So it's good to know. Okay, so ionization energy trends. Where's the trend? Do I have a trend? Here we go. So we'll go back to the second ionization energy level soon, but here's the trend. That the ionization energy increases across a period. And why is that? So ionization energy is the energy to put into an atom to release an electron. So let's say we have lithium, and you have a nucleus, electron. Then you have, on the other side of the periodic table, you have neon. So a lot smaller, the same electron. Now, lithium, the electron out here is not really, it doesn't really have much of an effective nuclear charge to the nucleus. So it makes sense that it'll be a little bit of energy to put in, and then it gets removed. But neon, it's very happy with its configuration because it's a noble gas. Once you get closer to noble gas configuration, and this makes sense based on everything we've learned, an atom does not want to get rid of an electron. So lithium, beryllium, they want to get rid of electrons pretty easily. Once you get over to the nonmetals, they don't want to give up electrons at all because they're getting very close to their goal, which is a noble gas configuration. So you could imagine that if you put in enough energy to force the nonmetals to give up an electron, it's going to have to be a hell of a lot of energy to offset the amount that it wants an electron. So does that make sense?
Yeah.
Okay, cool. Any questions? So that's explaining. No?
If you look at lithium versus francinium,
Yeah.
so francinium is going to take more energy still than lithium, but like obviously less than its noble gas counterpart.
So you mean fluorine? Francium's down here.
Yeah.
Were you talking about fluorine?
No, I was talking about francium.
Oh, okay. Francium's down here. So francium actually has less ionization energy than lithium.
Why?
So good question.
Oh, is it because the valence electrons are so much further out from
exactly. Yep.
Okay.
Yep. So yeah, so here's a chart showing the trend. If you look at francium's down here.
Yeah,
But, yeah, but cesium, same idea. So lithium, it's closer, and then cesium, that one electron will be way out in the 6th energy level, so it requires a little bit less energy to remove it, and it's a little bit. It's only about 100 or so off, and that's not much of a difference compared to the difference going to the right.
Yeah.
So neon definitely does not want to get rid of its electrons. Neither does any of these nonmetals.
Oh, now this concept isn't difficult, but like, oh my God, the elements that they put on in the questions are so annoying.
Yeah. So like they probably want you to, some of them are like compare like diagonal ones.
No, it'll give you like cesium, barium,
like this,
and then arrange lithium, carbon, oxygen. No, that's easy. They're all in the same row. It'll give you ones that are like
staggered.
Yeah, a couple in the same row, and then the 3 others are in completely different ones.
Yeah, so you have to use that's why I'm saying it's better to understand. You can figure that out by understanding the concepts of what takes precedence, what makes more of a difference energetically to the atom, getting bigger or getting closer to noble gas configuration.
Yeah.
For example.
So like a hard question would be like, it'll give you lithium, carbon, oxygen, and then it'll give you rubidium.
Right.
But like, I guess it's not that hard because like,
rubidium has less than lithium, and then everything else is more than lithium.
Okay, well, it'll give you like lithium, carbon, and then silicon, and then oxygen.
Right. I can see how that's difficult. So
that's a little harder.
Yeah. So you can know that. So now knowing precedence, knowing what takes these elements to the right, all of them are a lot higher than the ones on the left. Beryllium is whatever, but most of them are a lot higher. So you know that silicon is less than carbon, which is less than oxygen. Oxygen's the most. Carbon's the second most. Between silicon and lithium and rubidium, rubidium's the least. It's less than lithium. So silicon has to be in the middle.
Yeah, it's just a lot of
Yeah, it's a lot of thinking, a lot of reasoning. So yeah, chemistry is not easy. So this is part of the more difficult things. But if you understand the electron configuration, the nuclear charge, and what's happening as you go across periods, meaning the protons are increasing and going down, the orbitals are getting larger, then you should be able to use your intuition to try to get it.
Wait, we only did 2 of the 3 things so far, right?
Yeah, the third one is electron affinity.
Okay. And we talked about just before this the size of the
Yeah, the atomic radius.
atomic radius, and that gets larger across, but smaller down.
Correct. No, it gets larger down, smaller across. So the opposite.
Okay, yeah.
Yeah. So here's a good idea of it. As you keep adding protons, starting at lithium, you go smaller, smaller, gets closer together,
Yeah.
very tight. Then the next energy level comes in, big, smaller,
Right.
smaller, smaller, tight, and then that happens. Okay. Good questions. Okay. So now that we understand ionization energy, we'll talk about first, second, and third ionization energy. And this makes sense because what's going to happen is you can imagine removing one electron is going to require less energy than removing the second one and removing the third one. So ionization energy increases for every electron that you take away. But the way that it increases is different. So for every element, depending on the position of the element in the periodic table. So here's what I mean. Sodium, if you take away the and we'll talk about this on the periodic table soon. But sodium versus magnesium. Sodium, you take away one electron, very easy because it's one and it's there and it wants to get rid of electrons anyway. Then you get rid of the second one. It's 10 times harder to get rid of the second one. Then you get rid of the third one. It's still bigger, but I mean, sizable. Magnesium, the first one's easy. The second one is still easy. The third one's impossible. Why is this the case? We will look at the periodic table to determine that. Okay.
It's because of the orbital that you're trying to break, right?
Exactly. Yeah, you got this. You could, when I was 30 minutes late, you could have taught the first 30 minutes. All right. So let's look at sodium. You get rid of one electron, its noble gas or its configuration is noble gas. It would go back and it would look like this. The electrons would look like that.
Mm-hmm.
To get rid of a noble gas electron, we know is extremely difficult. But it's even more difficult because it's sodium. It has one more proton. This is 10 protons in neon, 11 protons in sodium. So it's basically going to be a super neon on steroids. It's going to have the electron configuration of neon, but it will have one more proton, making the charge that much more and the attraction forces of the electrons that much greater. So to remove an electron from that super neon is insanely hard. So it would require 10 times the amount of energy than it takes to remove the first electron from sodium. So that's why the second ionization energy is a lot greater. And the third one would be it wouldn't be a 10 times difference, but it would always be greater than the previous ionization energy. And magnesium, same idea. It's like you said, which orbitals are we taking away the electrons from? So magnesium, take away the first one, looks like sodium. Take away the second one, looks like neon. Pretty good. Once we take away the third one, that's impossible, or that's really hard. So that's where the huge jump in ionization energy would occur, would be the third ionization energy. So good questions that would be on the exam, on the homework is which of the following has a larger second ionization energy, calcium or potassium. And then you would see, all right, second ionization energy, first one for potassium's easy. The second one is insane. For calcium, first one's easy. Second one's pretty easy. Third one's insane. So we know that for second ionization, potassium would have a greater second ionization. Things like that. Okay, there are some little discrepancies in ionization energy. And this is, again, due to orbitals. So if we look at boron right here, we would expect the ionization energy to increase going to the right. Beryllium is 900. Boron goes down to 800, and then it goes up again. And we'll talk about oxygen in a second. But it goes up, then it goes down, then it goes up again. So the reason why is because of the orbitals that the electrons are filling up. So boron let's do one. It'll be 1s, 2s, 2p. All right, so here's boron. To remove an electron from boron, it only has one electron in the p orbital. To remove that electron would be pretty easy. The electron's by itself. It would create an entirely empty orbital. So that's why. That's why I wouldn't go. That's why it would be less than taking one from beryllium. So beryllium's configuration is 2s2. That means you're going to be taking an electron away from a completely filled orbital, where 1s2, 2s2, that's going to be pretty happy. So energetically, it would require a little bit more energy to remove that 2s, that second 2s electron, than it would be to remove the first 2p electron. So that's why you see a little bit of a dip. And that dip is pretty consistent going down the table, going from your S2 position, to your P1 position. See, this decreases a little, but then it increases again. It's really not much of a difference here, but it does increase again. That's where the energy levels become so close that whatever. But generally for the lower number elements, that's true. And the same thing is true for atoms like oxygen. If you compare nitrogen to oxygen, you would expect it to be the oxygen ionization energy to be higher than nitrogen because it's closer to a noble gas configuration. This is not true because, again, of orbitals. So oxygen's configuration is 2p4. So 2p4. So same concept. To remove this electron, this one right here, it would require less energy than removing nitrogen's electron, which is right here. So removing this one would create a half-filled orbital, which half-filled orbitals are cool, or fine. I mean, by cool, I mean, and the atoms like them, and they're energetically stable. But if you remove one from that, which nitrogen would be doing, so nitrogen is 2p3, which is, once we get rid of this one, is this electron, that would require more energy because it's already at a happy level, a happy state. Then removing that other electron would not be that favorable. So kind of the same concept. Okay, any questions? And here's the same thing with ions and stuff, whatever. All right, so the last thing we're going to cover, and whenever towards the end we're covering metals and different things, we already kind of covered that, just general information. But the main thing we're going to cover, the last thing, is electron affinity. So electron affinity is the energy associated with the gain of electron. And I hate that they use the word associated. And really what this means is the energy lost while gaining an electron. So to remove an electron, you need to put energy into the system. You put energy in, and the electron gets ripped off. To add an electron, energy needs to be lost from the system. So it's the opposite reaction. Now, the meaning, it's important lost because they're all going to be negative. So it's going to be weird. So when I say increasing, decreasing, it might be weird. Now, when it says the electron affinity increases across a period, that means, and it's kind of the same trend as ionization, but what I mean by it increases is the absolute value increases. Meaning it gets more negative going across the table. So this makes sense because as we get closer to a noble gas configuration and we get more protons, the atom wants to gain electrons more. So if we look here, if we look, I don't know, let me get another page up. It says electron affinity trend. Here we go. So I'm going to share my screen, my new screen real quick. Right, no. All right, so you should see the Chrome screen. You see electron affinity. It increases going to the right, and it increases going up. So basically, which elements want electrons the most? It's going to be everything up here. And technically, the noble gases don't have an electron affinity, or theirs is, where is it? Yeah, so not including noble gases. So if you look at the trend right here, it's kind of weird. It's not really a trend, but it is. So as you go from left to right to your halogen, we know the halogens are the most reactive, and we know halogens want to gain electrons more than any other element. So it makes sense when you go to the halogen of fluorine, it has the highest electron affinity, meaning the most negative. You see how it's going from 0 to negative 400 this way? So it's the most negative, meaning the most energy is released if you gain an electron. That's good. If you release energy, that means the atom is going to have less energy, and it's going to be more energetically stable because everything wants to be at a lower energy level. So fluorine gaining an electron makes it happy, makes it at a noble gas configuration, meaning it will be the most energy would be released in that process. Then as you go from the next sodium level, it increases again going to the right, and then chlorine's the highest. And you see how the noble gases are the lowest. Neon, argon, zinc is pretty low for some other reason. And then, well, probably because of its orbitals that have filled up. It's not, zinc actually gains energy when you remove an electron because it doesn't want to, a lot of these, the ones that don't want to that don't want to gain an electron, if you force them to gain an electron, you have to put energy into them to gain an electron. So that's true for the noble gases and some of the other ones that are in already filled orbitals, like zinc, which is in a 3d10. So it's already filled up. To add another electron to it, it actually requires more energy to start the new p shell, to add an electron to the new shell, to the new orbital. So generally, that's the trend. Same thing with mercury over here and cadmium. So yeah, does that make sense? So electron affinity increases going to the right, increases going up. Up to the right is the highest. Well, really, chlorine's higher than fluorine by a little bit, but the halogens are the highest. That's the most important thing. And then a lot of it, there's little nuances like, and also not including noble gas. Noble gases are the lowest, but this is why, another reason why I stress to remember effective nuclear charge, remember the orbital notation, and remember which electrons you're removing or adding when you're dealing with all of these trends, because that'll help you. If you do an example of copper and zinc, right? From the trend alone, you would think, oh, zinc has a higher electron affinity than copper. That's not true. Copper has a higher electron affinity than zinc because copper, based on its orbital diagram, has room for one more electron. And that electron will actually go into the 4s because copper's configuration is 4s1 3d9 or 3d10. Zinc does not have room for another electron. Its 4s and 3d are completely filled. Therefore, it would actually require a lot more energy to put into, or it would require a gain of energy to put into to actually make electrons at the 4p energy level. So by more, we mean absolute value. So we mean more negative. That's what we mean. Increasing electron affinity means the numbers are more negative. So that's weird, but that's true. Because you know that gaining an electron means that means energy is released. It's exothermic. Okay, we're going to go back to the slides now. All right. Any questions on that?
So no matter where you are on the periodic table, it should follow that trend, right?
No. So it's a very loose trend like we just saw. So here, like this chart shows you.
Can you
So
just
I would
explain
say,
the zinc example again? Like I got kind of lost.
the zinc example?
Yeah.
Okay, good. Yeah, good question. Okay. So I'll use zinc and copper. I'll write them down on here. All right, so copper, and here's zinc. So we know that zinc's configuration is 4s2 3d10. Copper's configuration is 4s1 3d10. Right? So electron affinity. If we want to give copper an electron, it's pretty easy, right? Oh, okay. Give it an electron, it releases some energy. And like 4s1 to make it 4s2 is some amount of energy. So it requires some amount of energy. And that it would release energy. So adding an electron releases energy. So it would release energy. And that's good. That's a favorable thing to do. So
Okay.
Releases energy. Zinc. If we want to add an electron to zinc, we can't add it here. We can't add it here. We'd have to make an entire new level. It would have to be we have to open up the 4p1 to give it an electron. That actually requires energy to be put in. Adds energy to keep it there because that's very unstable.
Okay.
So this one's easy and it releases energy. This one's hard to do, really hard to do, and it adds energy. So that's not good.
And electron affinity is how likely it is to release energy?
Yes, but how likely it is to gain an electron.
Okay.
So things
Oh,
that
so
have,
even
yeah.
okay.
No.
So even though like both the arrows point to the upper right, that would mean that you would think that zinc would have a higher one than copper, but that's not true.
Exactly. Good. So there are cases like that. So
is it only the ones when we talked about the same thing, like from the last thing?
it's kind of the same concept, yeah. It depends on their orbital. It depends on where the electrons are being gained from on their orbital.
Okay.
Yeah, so you have to take that into account when dealing with any of these because the trend, as you can see in this chart, is very loose. So like
the trend is depends on like the orbitals.
Yeah, but in general, this is true, but it's not really true. Like it's weird. But so let's look at this chart again. We'll look at copper and zinc. So zinc's down here. Copper is up here. So copper's all the way here. So it's pretty easy for copper to gain that electron, and a decent amount of energy is released.
Mm-hmm.
In order for zinc to gain that electron, you actually need to put more energy into zinc, which is not favorable to make that electron be added. So yeah.
So what about fluorine and potassium?
Okay.
Fluorine's the most. We know that.
So fluorine is very easy to add an electron, 7A. It has one more spot left over. It'll release a lot of energy, and it's very happy doing that. So releasing energy is good.
What about boron and like beryllium? Okay,
so boron, good question. So boron, so you would think by what we know, beryllium will not have a very high electron affinity because it would need to open up a p orbital to gain that electron. And boron, you would think it would have less of an electron, more of an electron affinity because it's already open. So let's look at here. Boron's here, beryllium's down here. So beryllium, exactly the point, it's not that happy gaining another electron. So it's actually in the positive. It's all the way down here. And then boron, you already have that 2p1 open, so adding another one wouldn't be too much of a big deal. So it does have a higher electron affinity. So that works. Yeah, so it's a very loose trend. You have to look at where they're located. And if they're opening up a new orbital, that's a negative. That's not good for electron affinity. That means the electron affinity is low. I guess we'll write that as a key rule. So we'll say if you open a new orbital by adding an electron, this means low electron affinity, meaning the absolute value is low, not the number, because, these are all negatives. Okay. Make sense?
I have a question.
Yeah. What's up?
Can you go over how you got the 4s1 and 3d10 again? Because I counted and I only got 9 for D.
Right. So for copper?
Yeah.
Okay. So that is true. But remember, copper is one of the exceptions. So normally you would think 4s2, 3d9, right?
Right.
That's what you got. So that's what you would expect. But what is actually true, based on the molecular diagram, the orbital diagram, is that a d orbital with only one spot left is not as energetically favorable as it filled up. So what that means is copper would rather take one electron from the S and put it into the D to make it 4s1, 3d10.
So how are we supposed to know that?
Good question.
Buddy.
So that is true for where am I at? That is true for
Anything that's halfway or getting filled in its orbital.
Yeah. So that phenomenon is true for the D4 and D9 elements. So as we went over before, where chromium and molybdenum, whatever that is, they take an electron from the 4s2, make it 4s1, 3d5. Because if you write d orbitals, I'll do it up on the top left. And having 4 electrons in the d orbital is not very energetically favorable. If you have an s orbital that has 2 filled already, it makes more energetic sense to take one of these electrons away, because they are repelling each other.
Mm-hmm.
Take one of them away, putting it in the open spot.
Right.
So that's why it's 4s1, 3d5 for these. The same thing applies to the D9 elements, copper, silver, and gold, where you have the same case, but instead of being half filled, they want to be totally filled. So you want to take this electron again, move it to the open spot, and make it filled, and then have one space open in the 4s.
Okay. Another quick question. I don't know if this was answered before. I wasn't paying attention.
Okay.
But when we go to the d orbital, why do we skip the p orbital? So like for...
You mean in terms of the numbers?
Not the numbers. So if I take iron, for example, which is Fe, it's 4s2, 3d5, or 3d6, right? Right. But there's a p orbital in between, no?
No, the p orbital came before it.
I see what you mean. There's a p before. So
because it goes SPDF, right?
Right. In terms of increasing energy, it goes SPDF, but when we went over configuration in the beginning, I said to read it like a book. So if you go through, see what you go through first. Some p orbitals are higher than some d orbital. You can see how maybe this d orbital, where iron is, 3d, has a higher energy than 3p and 2p.
Mm-hmm.
But it has a lower energy than 4p, 5p, and 6p.
Okay, yeah.
Right. So the way you would count would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6.
Okay, so just read the periodic table for that then.
Exactly.
Okay, fine. Okay, thank you.
All right, no problem. Okay. Cool. So that's basically it. Everything else in the chapter was just like information. Like if you add this to this, it makes this. Like we kind of went over all these things already. Different types of reactions. Yeah. So trends in noble gases. We talked about noble gases already, where their ionization energy level and ionization energy is very high. So they don't want to get rid of their electrons. Their electron affinity is also very low, meaning they don't want to gain electrons either. They don't want to do anything. So yeah, and the thing about affinity means you like something. So if you have an affinity for something, that means you like it. If you have a low affinity, that means you don't want it and you don't like it. So noble gases, it makes sense that they don't want to do anything. So they have a high ionization energy, meaning it takes a lot of energy to do that. And they have a low electron affinity. Low boiling, whatever, all that stuff's whatever. So yeah, that's basically it. Here's another example. Here's ionization examples from the homework, but that's basically it. So are there any questions? And since I was late today and I feel bad about it, I'm going to put you into breakout rooms, but you don't have to like stay and you can do whatever you want today, basically. So like, whatever. I see someone left already. Whatever, you do whatever you want, but still the homework is due tonight. So what was that?
No.
Okay. So I will, if there's no other questions, I will start the breakout rooms. I'll do 4 of them. I'll do 3 of them. 3 of them, just so if people leave, nobody will be alone. And if you're alone, I guess you could just ask me for help or do it somehow. I'll be here till 12. Okay, so if no other questions, then I will start those rooms.